In this video, we're going to look at how to find the area between polar curves. And it's as intuitive as it was in rectangular, so I'll just remind you, in rectangular coordinates, we were trying to find area between curves, where, for instance, we might want to find this area here. And so the strategy was to find, I guess I'll try some more different color here. Like you wanted to try to find the area under f of x, which would be like all this. And then you want to minus the area under g of x, which would be like all this. So like you think, and so what that does is it gives you these two integrals, but by properties of integrals, since they have the same limit of integration, you can write it like this. And so we think, top function minus bottom as like a nice rule of thumb to find area in between curves in rectangular. So in polar, it works similarly, except you don't want to think, you can't think, top minus bottom, because the way polar area is accumulated, you have sort of an outer function, so that's f of theta, and then you have an inner function, which is g of theta, and so again, you'll accumulate area, let's just say from theta 1 to theta 2, we're going to accumulate area inside f of theta, which would be like all this, and then you're going to subtract. Right, so this would be like the outer area, and then you're going to subtract the inner. So this is outer, right, and this is clearly inner. So now you just subtract the purple, and you'd be left with this area here. So the rule of thumb we use is area of outer minus area of inner, and remembering that we have a formula now for area in polar. So the area of the outer would be 1/2 the integral from theta 1 to theta 2, r squared, so I'll use the notation up here. Outer is f of theta, so outer squared minus the area of the inner, and again, by properties of integrals, since you could factor out a 1/2, these have the same limits of integration, so as one integral you could always do it like this. Okay, so like in a calculus formula sheet, you'd probably see that. So we'll do one example here where we're going to just set up the integral, and then in another video we'll do one where you have to do a little hunting for the limits of integration using your calculator. Okay, so let's say here this is a delta math problem. So this says let r be the region inside the polar curve r equals 5 plus sine of theta, and outside the polar curve r equals 5, as shown in the figure below. What is the area of r? Use a calculator to evaluate and round to the nearest thousandth. So again, I'm going to ignore the calculator part for now. We're just going to set it up. So I got my formula over here in the box. And again, if you want it as a visual, I've set it up here. Let's go to Desmos. So what I'm going to show you basically is if you let's reset these to 0. Right, so the area of the outer is going to get accumulated there. It seems pretty obvious that it's going to accumulate from 0 to pi. And then we're going to subtract the area of the inner here, which would get accumulated again from 0 to pi. And so we want the area of that, green that's left. Okay, so let's go do it. Call this r. All right, and so the language in this problem kind of tells you essentially which curve is which, but let's just label it, right? So r equals 5 must be the red, because the language is telling us that we want area inside the polar curve 5 plus sine theta, and outside the curve r equals 5. But let's just check, a circle should have a constant radius, so go in both directions. 1, 2, 3, 4, 5, that's here. 1, 2, 3, 4, 5, that's there. So that's clearly, right, so the red is clearly the circle. The red circle would be r equals 5, so you might just label that. And then this is r equals 5 plus sine of theta. Okay, so we can tell this is our outer, and r equals 5 sine of theta would be our inner. Notice that's only the case on the interval 0 to pi, because if we were to get if we were to try to find this area down here, I'll erase this in a second. Let's say we wanted this area here, the roles would switch, right? Because the circle would now be the outer, and the limacon would be the inner. Okay, so in any case, we're just going to jot down the expression here. So our area would be, we'll just write down our rule of thumb, outer minus inner. So our outer would be, again, the limits of integration are 0 to pi 1/2 r squared, 5 plus sine theta squared, minus the inner, which would be 1/2 0 to pi. Okay, or alternatively, using a property of integrals, 5 plus sine theta squared minus 5 squared. All right, so if you're going to do this on the calculator, just a quick reference to what you do in the calculator. I would probably put this into I'd put that into y1, I'd put this into y2. Make sure you're in radians, and then on your home screen do integral of y1 squared minus y2 squared. I mean, it's just 5, so maybe you don't need to do y2, but as a general approach, and then just multiply by half, and you'll get it. So there's an example of area between curves, and another example we'll do one where the limits of integration are not so obvious.